Welcome everyone. In this session, we are going to see what is a function and how to adopt functions for Verilog modeling style. A function is like a subroutine or a procedure in a program. It is defined separately within the main module and not after the end module. It should be defined before the before the end module, but anywhere in the main module. And once you write the function, you can call it whenever necessary. Whenever a function is declared with a function name, the system will allot a register to it. That is how a function is going to work. System is allotting a register to the function, defined function. And the name of the register will be that of the function. Whatever is the name of your function will be the name of the register, and its type, data type, as well as the size will be the same thing what is there in the function. Suppose if the function is 2-bit, the register that will also be 2-bit. Now when a function is called, the system executes the function activity and generates the output. Now here I have the general syntax of the function. Function, type or size of the function. So function is the keyword, function declaration. Type or size, the function can return a real or an integer data. It can be a vector of a specified size. This is of 1 down to 0, 2 down to 0, whatever we write. And if it is integer, this is optional. There is no need to mention it. Then we have the function name. Inside the function, we will be having input declarations, local variable declarations, procedural assignments, all the logic involved. You can write end function. But this function should be defined within the module, and you have to, it should be within the end module. Now, what is the scope of a function? Now, a function can have only input arguments. You can only give input arguments to the function. Now, if you give only the input arguments, the function will generate some output. Where will the output be defined, you would have thought? Now, when you give input arguments to the function will save the output in the function name. But we already have told that function name is stored as registers. So in the register of the relevant output size, the output will be stored. When a function can have multiple input ports, when a function with multiple input ports is called, the order of the arguments in the calling function should match with the order of the arguments in the called function. Similar to what we did in instantiation, when we declare the module and we define the input and outputs A, B, C, and when we instantiated that in the gate level model, we spoke about order matching, port matching. So the port should match properly. A function will return an output port. There is no separate output port. In function, we will not define any outputs. We will only be having inputs, but output, the function name itself will return the output. Within a function, you can define variables and use it, and these variables will become local to the function. Function can be defined anywhere within the main module, but before the end module. You cannot use event or timing based controls, which means always at pause edge clock, always at neg edge clock, always at preset. All those are event control signals. We cannot use event control. This function is similar to gate level model, we can assume, but it is not exactly that. It is similar to that. This restricts the function of the combinational circuits. So since we cannot use event or timing based controls, function can only be adopted to combinational circuit. We cannot adopt it to sequential circuits, because whatever sequential circuits we have observed are memory elements. And for memory elements, event control is important. Event control is nothing but a clock. The function can be defined anywhere within the module. A function can also be called from another function. A function in a module can be called from another module if you give proper referencing, hierarchical referencing. And a function can be called repeatedly. Now what we'll do, we'll take an example of full adder using function. I'll take an example of full adder using function and I will show that for you. Now let me write a program for full adder using half adders in function. So when we write a program for full adder, the inputs for full adder will be module full adder. What are the inputs? My inputs for full adder, okay, first let me write the output S and C out. The inputs for the full adder is A, B and C in, okay? Now, what is my input? I have to define it. Input A, B and C in. And next I have my output. Output S comma C out. Now when we are designing a full adder using half adders, you will get three intermediate signals. One is your sum intermediate, one is your C1 and C2. So let me recap that full adder diagram for you. Now you can see that this is a full adder with half adder, which we have already done. In this full adder with half adder, I have A, B and C as the inputs. Here I have the intermediate sum. This is an intermediate sum. Here I have an intermediate sum and this is an intermediate carry. This will give you the original sum and I have the intermediate carry over here. So what we have done, I've labeled this sum intermediate carry as C1. This intermediate sum we have labeled over here as SI. And there is an intermediate carry over here. This I've labeled it as C2. Now using this, we are going to use this and adopt it in our full adder modeling style. And I have an half adder or gate also. Now here, what are the intermediate signals I have? I have intermediate signals as wire C1, S1 and C2. These are the different intermediate signals. Now I am writing a function for half adder. This program is to implement a full adder using half adder as a function. Okay, now we have to write the function. Function can be written anywhere within the module, right? So I'll write the function first before I call it. Function. The syntax for function is function. So this function is written for half adder. There are no outputs in the function. So what is the bit size of the function? Half adder will return two outputs. One is the sum, one is the carry. So I'll take sum A and carry as the intermediate signals. So the size will be 1 down to 0. There is no need to declare the outputs in the half adder. Now what are the inputs to the half adder? Input to the half adder will be A and B. These are local variables. You can leave it as A and B or I can give some other name. So I've given A and B. Now how will the half adder function? Now half adder itself is a register. We know this half adder itself is a register which is storing the output. Outputs are not declared as separately. And this is 2 down to 0, which means I'll be having half adder of 1 and I'll also be having half adder of 0 bit. Half adder of 1 and half adder of 0 bit. In half adder of 1, what we are going to store, in half adder of 0, what we are going to store. So I've written half adder will be equal to the function name, which means that output is equal to sum and carry. A and B is the carry. According to half adder equation, C is equal to A and B and sum is equal to A XOR B. We know that already. So the same thing I followed and I've written output will be equal to, output we already know it is 2 down to 0, A1 and B1, that means half adder of 1 is equal to carry, and A1 XOR B1, which means half adder of 0 will be equal to sum. So I followed this and I written the half adder function. Now end function is done. Now we have to call the half adder in the full adder module. So continuation. So when we call half adder in the full adder module, 2 times we will be calling. It will generate 2 results. Okay. So now what is the output generated from the first half adder in full adder? We will be having in first half adder C1 and Si according to the diagram what I've shown. C1 and Si. C1 is the carry of the first half adder in the full adder diagram. This will be equal to half adder of, what are the inputs I'll give to the half adder? A and B. To the half adder module, I'm passing A and B. I'm getting the inputs intermediate sum and carry. This is the first function. The next function will be, what is the second half adder generating? It will generate C2 and sum directly it is generating. So I can write directly sum. This is equal to half adder. What is the input you're going to give to the next half adder? One is the sum and the other one is your C in. So second half adder is done. I also have an OR gate. Okay. How will I implement that OR gate? I can write just a gate level model and show the OR gate. What is carry out equal to now? Carry out is equal to C1 or C2. So I will give C1 or C2. Now this is as you can see, it is something like a data flow model program. So I will write assign Cout is equal to C1 or C2 end module. So that's all. This is all regarding full adder using half adder as a function. Now you can write the test bench for that. It's the same test bench whatever we are using for a full adder. You can write and we can observe the results. So the next example what I'll be showing for the full adder for the function is a ripple carry adder. So we are going to use full adder as a function and write the ripple carry adder program. You're going to see a ripple carry adder. Let me take a 4-bit ripple carry adder where full adder is defined as a function, and in turn full adder is calling the half adder as a function. Now for a ripple carry adder, what do we have? We again will be having the inputs A, B, C in. C in I will take, and I'll have the outputs sum and C out. This is a function for module for ripple carry adder. We already know what is a ripple carry adder. The 4-bit ripple carry adder, so input 3 down to 0. So my A and B is 4-bit in size, and there is one more input C in, which is 1 bit in size. Then I have my output. Output is, what is the size of the output? 3 down to 0 because it's a 4-bit ripple carry adder. 3 down to 0. Yes, and I have my C out, output C out. These are the declarations for the inputs and outputs for the ripple carry adder. Now I want to implement a ripple carry adder using a for loop. So what is a for loop? A for loop can execute a certain number of expressions in number of times. So here we are seeing a for loop. The syntax for loop is for assignment 1 expression, assignment 2, and then we have the statement. The for loop will be having 4 parts. The sequence of the execution will be as follows. The first one, it will execute the assignment 1. It will evaluate the expression. So this is the first term will be the assignment. The second one will be the expression. If the expression evaluates to 1, it will end actually. Now if the expression goes to 0, if the expression goes to 1, it will keep on repeating the steps. If the expression goes to 0, it will end. That depends on how you give. 1 and 0 is your choice. You may follow forward forwarding or reverse forwarding. So that depends on your choice. Now, for whatever we are doing, if the expression evaluates to true state, it will continue with the execution of the assignment. If the expression evaluates to false state, it is exiting the loop. So in this diagram, you can see assignment, expression, execute, execute until the condition is satisfied. It will keep on executing this right side of the flowchart. Once the condition is satisfied, it will end the code. Now, the same ripple carry adder coding what we are doing, we'll first implement it using a for loop, and then we'll go for using a function. Now first let us implement this using for loop before going to the function. Now whenever you implement a for loop, it should always be written within an always at some condition should be there. So what I'll do, I'll give an enable, always at enable, and I'll declare one more input as enable. I'll be having one more input as enable. Always at enable begin. So 4-bit triple carry adder for I is equal to 0. 4-bit means 0, 1, 2 and 3. So I less than 3. I less than or equal to 3. I is equal to I plus 1. Now again I declared a variable I. So that I should declare. Now if you can see, I is taking the values 0, 1, 2 and 3. Since I is taking the value 0, 1, 2 and 3, I can declare it as an integer because it is an integer. For I less than or equal to 3, I is equal to I plus 1. Now what is the next thing you have to do? For loop will generate intermediate signals. We already know a for loop will generate, for ripple carry adder will have intermediate signals, all the carry. So I will assign, before I'll assign, and before that one more thing I will do. I will give wire. So initial carry is C0. So I will give from 0 to 4 or 4 down to 0 C. Okay, and initial carry is what? Assign C of 0 is equal to C in. So C in is equal to C of 0, and I will assign what is C out is equal to. C out will be equal to my last carry, C of 4. So this is my assignment. Now for I is equal to 0, I is equal to I plus 1. Now what is that you're going to write inside? So we are going to see how it is working. So my full adder will have two outputs, C out and C. So this I will write it as Ci plus 1, which is nothing but the carry output and sum. Carry output and sum will be equal to, carry output and sum will be equal to what? A plus B plus Ci. So I can take AI plus BI plus Ci. What does that mean? This means I will add A of 0 plus B of 0 plus C of 0. C of 0 is my input carry, and I will generate the output C of 1 and sum of 0. Right? This is for the first step. If you write it for the next step, when I is equal to 1, I'll take the input A of 1, and the other input will be B of 1, and one more input will be C of 1. How did I get C of 1? C of 1 is generated in the previous state, and this will give me my output C2 and S1. So for that reason, we have written, if you can see clearly, I is starting from 0. Next I will be equal to 1. So it is AI plus bi plus ci. So ai plus bi plus ci. I'll get c1 and s0. So this is followed up to 4 steps. This is for. I can also give one begin and end since it's a for loop. Looping, it is good to follow indentation in loops. So I've given one begin and I've given one end. This is all with respect to for loop program. I've already assigned your output also earlier itself. Assign cout is equal to c4. Then you can end the module. So this is ripple carry adder using for loop. Now to implement this using function, I'll write the function code. Now this is the modification for this full adder code, ripple carry adder using function. So what happens, I'm calling the function for which I'm passing the values a of I, if you can see line number 26, a of I, b of I and c of I am be passing. And then I have to write the program for function for full adder. Then write down the function for half adder and then give an end module. It will work. So this is how it looks like. Function for a ripple carry adder, the only modification will be there in this part where I have to call the function name for full adder. Write the function for full adder. You can use any logic. Here we can see that function 1 down to 0 is the full adder. Input ABC. Register I have declared A1, 2 bits for A1, 2 bits for A2 and 2 bits for A2. Where A1 is equal to, A1 will be equal to my carry and sum, that is my C1 and SI. And my A2 will be equal to my C2 and my second sum. So that is my exact sum. But here I have not written as sum. This sum is written as A2 of, this sum is written as A2 of 0. My A2 is the second full adder. It will generate C2 and my S. My S is nothing but A2 is equal to C2 and S. And what is the input? A1 is taking the inputs A and B. A2 is taking the inputs, whatever is the sum from the previous stage SI, which is nothing but A1 of 0. So one input will be A1 of 0 and the other input will be C. Taking these two inputs, it is generating the sum and carry. Now, what are the two different carries? What I'm getting the carry over here, A1. So this C1 will be equal to A1 of 1. A1 of 1. And C2 will be equal to A2 of 1. A2 of 1. So final carry is A2 of 1. This is final carry. A2 of 1 is equal to final carry. I'll write it as Cout. Cout is stored in variable A2 of 1 and this is equal to C1 or C2. C1 or C2, which is nothing but what is C1 from the first half adder? From the first half adder, C1 will be equal to A1 of 0. So it is A1 of 0, A1 of 1 and it is ORed with A2 of 1. The program can be edited using these steps also, whatever is written as comments over here. And what is my final sum? My final sum is equal to A2 of 0. So now full adder, what is full adder equal to? My final full adder, which is 2-bit in size, will be equal to A2 of 1 and A2 combined. Now this full adder is implemented using half adder. Again, half adder is taken as a function and write the end function. Now if I save and if I simulate the test bench, we have the test bench over here. If you can see the test bench, I've taken two cases. One case is 0 plus 1. I've made cin as 1, enable is 1. That means it is activated. The next case is I'll make it as 1, 1, 0 and 1, 0, and cin is 0. Now if you see the simulation output, so let me run and see the simulation output. Save. So this is the waveform what we have got. So if you can see the simulation results, initially A is 0 and B is 0, 0, 1, 0. If you add, you will get the sum as 0, 0, 1, 0. And I've retained enable as 1. So this is the second case, 0, 0, 1, 1 plus 0, 0, 1, 0. We'll get 0, 1, 0, 1. 2 plus 3 is 5 with no C out. And I've retained. You can give other test cases and also evaluate this module what we have written. Thank you.